So we're going to have a quick lab today where we talk about KNN classification again. And we're just going to finish up some of the things that we had talked about last time and look at some evaluation and some nice visualization of KNN classification. So last time we had worked with this iris data set, and let's just rehash through that. So we're going to kind of continue off in this lab with where we had left off last time. We were working with this iris data set, and it had information on sepal and petal length of 150 flowers from 3 species of iris, Setosa, versicolor, and virginica. And we looked at some summary information, and we wanted to build our first classification or classifier, a KNN classifier. We wanted to predict the type of flower, the species of the flower, from our features. And we can build KNN classifier. We load up the class library, and the function is KNN to build up the KNN classifier. So it's K nearest neighbors classification. You can read the help page. And what we had done last time is we had subsetted, and we'll see why today we want to do this. We subsetted to just 2 x's, x1 and x2, being sepal length and width, and species being our class. And so we had subset down to this data set. And the reason we want to do this is because it's going to be easier to visualize in a 2-dimensional space. And we had then done a test train split, or test validation split, however you want to think about it, and made our training x, training y, our test x, and our test y. We had built the model, and we had predicted the class, and we had just gotten to the point of kind of evaluating the predictions. And we had seen that our accuracy was about 76%. That is 76% of the time we were correctly predicting the class. So let's kind of pick up here, and let's look at evaluation metrics. And one evaluation metrics we had looked at was the confusion matrix, and we can look at confusion matrices in the caret package. There's a function called confusion matrix. So we load up caret, and we can look at the help page for confusion matrix. Takes in the data, takes in the true values or the reference values, and it's going to give us back a bunch of information on the accuracy. So we can make our confusion matrix. C matrix is confusion matrix, and data. So I guess our predictions, so before we do this, right, our predictions were pred. Right, is that right? Nope, what were our predictions here? All the way back up here. So you can actually collapse these things with that button. Our predictions were predict y, and test y was our y's. So data here, I'll pass my predictions, and as my reference, I'll pass in the truth, test y. Test y without a space, underscore. Well, that's an error to get. Let's see if we can fix this. So test y, predict y. It says something about this package is required. So let's install that real quick. Okay. Are we lucky? There we go. Okay. So if we first look at, you can always just call the function names on anything, and it'll give you the elements of that object. So here we have positive table overall by class mode dots. So table is our, table. So you see there, I didn't actually complete table. R's are a little too loose in its dereferencing, and so you actually, like, as long as it's uniquely, there's only one element here that starts with TA, which would be table, so it actually completes it. It's bad programming practice to do that. You should always write out the full name. But C matrix table is our confusion matrix. And so again, our confusion matrix here tells us on the diagonal the kind of correctly classified points, and the off diagonal are the incorrectly ones. So the prediction, they may have written it reverse in the notes, doesn't really matter. Here the reference is the columns, so these are the true Setosa, true versicolor, true Virginica, and the rows are the predicted ones. So among things that are truly in Setosa, we predict 30 out of apparently 30 of them perfectly correctly. So we get that correct. Among things that are truly versicolor, we predict 23 of them to be versicolor and get 11 wrong. We predict 11 of the versicolor to be Virginica. And among the Virginica, we predict pretty much nearly identically the opposite, where we predict 23 of them correctly, 12 of them to be versicolor, and we accidentally predict one of them to be Setosa. So the confusion matrix really summarizes everything here. C matrix, or confusion matrix functions in this object C matrix does give us a lot of information. So not only if you just print it out, it will not only print out my confusion matrix, but it'll give me other statistics. It gives me accuracy, which we said was 0.76. It gives me the confidence interval for that, p-value, and there's a whole bunch of statistics. Some of these I don't even know what they are. Sensitivity, specificity. If you're taking do one, that would be something you might be familiar with. But there are other kind of accuracy metrics here. You see it also gives these by class. So it's class Setosa, class versicolor, class Virginica. Our Setosa accuracy metric is about its balance accuracy. So accuracy is the balance here means they do some little things to it, but it's basically perfect. Our versicolor is about 75%, and our Virginica is about 75%. You could always calculate these independently. So I could say, if I get a diagonal of my confusion matrix, right? Setosa, versicolor, Virginica, and I divide that by the sum, this would be my well, let's put it this way. This is my overall accuracy. Overall accuracy. If I take the sum of the diagonal of my confusion matrix, right, and then I divide through the total sum of that matrix, this should be my overall accuracy. That should be 76%, which is what we saw before, right? But you could also you could look at per class, and if I divide it by the column sums, this should give me my per class error rates. This is per class, and let's just round these to, let's say, 5 digits. So Setosa, as we saw from our confusion matrix, we get these all correct. And then for versicolor and Virginica, we get about 67 correct for versicolor and 63% correct for Virginica. So there's lots of different games and lots of different things you can play with a confusion matrix, and it's kind of the definitive way. You can also get other metrics out of this. I really like the C matrix function, or this confusion matrix function from the care package, because you can use it to get other things. So I can do C matrix, let's say names, C matrix, right, where there are possible names. So if I do by class, this is going to give me a whole bunch of different metrics. So F1, recall, precision. You might have heard of some of these before. Of course, there's simple ones like accuracy, sensitivity, specificity, that kind of thing. So this is the by class. You could also do C matrix overall, and it'll give you overall metrics. So C matrix overall accuracy. Is that going to give it to me? Oh, you know what it is. It's a named vector. That should give it to me. So there's my accuracy, right? So it pre-computes it for you. It's good to know how to do these by hand, but it's not too hard to compute. And in practice, what you're going to use something like this. So you can get all sorts of different metrics out of it. Okay, so that's kind of evaluation metrics there. And let's do some visualization. There's a fun idiom, and I'm going to use this throughout the course to plot some of our classification. Labs, some of the output from them. Okay, so let's go grab our model up here. What was our model that we fit last time? Where did we do that? Data set, train test. Okay. So here is where we built our model. Okay. And let's just set that aside for now. What we want to do is I want to plot, since if you remember, say my training X here. My training X only had 2 variables. So let's look at this again. We had sepal length and we had sepal width, right? And so we could actually, oops, I printed that twice, haven't I? We can actually visualize it in kind of a 2-dimensional space. And so let's do that. What I want to do is I want to make a grid first. I want to make a grid so I'm going to evaluate my classifier on this grid, and it'll give me a nice visualization. So first I'm going to get the range of, let's say, train X. You know what, let's even grab the original data set, right? So iris was the original data. Let's use iris. Let's not split it. So if I grab I think I would work with sepal length was the first one, and X2 was sepal width, right? Okay, so these are going to be my ranges. And then I'm gonna generate a grid here. So I'm gonna do this. I'm gonna generate a sequence. And I'm just gonna, so here's where X1S is. It's just a sequence from my minimum to my maximum. And so of some resolution of a grid. And I will do a similar thing, and I'll call it X2S. X2S, which is going to be a sequence of, X2, my sepal width, so X2S would be something like that. And I want a grid, and the way I can do this is I can call, so that grid is expand grid, and I'll pass it my 2 sequences. And well, let's just look at what this thing is, right? So it's just going to be a grid of all kind of pairwise combinations of these things. If I were to plot this grid, I think I need to load up, let's say, load up the ggplot package so we can plot things, and I could say ggplot, I'm going to pass in my data as my grid, and my aesthetic mapping, my X variable will be the first one, my Y variable will be the second one. Okay, let's just plot this real quick. So all I've done is generated this grid, right, of points at some resolution. You can do a finite resolution, it would take longer to evaluate, but it doesn't really matter. We've generated this grid. And I'm going to go and evaluate my classifier in each of these points, and we'll get to see I got a cool, we call decision boundaries of this thing. So what I need to do now is basically evaluate my grid, or my classifier in all these points. And the KNN classifier, so basically what I need to do is I need to change what my training y is, I'm sorry, what my testing x is. I said I'm training y. My testing x, instead I'm going to have that as my grid. Of course, it needs the right names, probably. Maybe it doesn't. Let's try this. Is this going to work? It's going to blow up. Oh, it works. Good. Okay. And so I'm just going to make, I'm going to bind these together. My predictions on the grid with their predictions. Call it grid prid. Okay, so I have my grid points and I have my predicted class at these points. And I should probably name these things better. What was it called? X1 was sepal length, X2 was sepal width. So let's grab this, sepal length, sepal width, and the last name here. Oh, this is not the syntax. Okay, let's make the last name here Fred, favorite one. Okay, just going to rename those columns so they're more meaningful. Okay, so I've predicted with this model. Is it a great model? I don't know, but it's a model. And what do I want to do? Now I want to just plot it, right? So I can ggplot, I'll pass it. Is that what I named this thing? Gridprid. And my aesthetics are x is sepal length, y is sepal width, and I'm going to make my color the prediction. And I can do kind of colored tiles with geom tile. I don't want this to color, I want the fill. There we go. Voila. So there it is. There is my super cool picture, right? So this is my kind of X space. This is my X space. I have two X's. This is the whole reason I subset the two X's, because I can make it plot in 2 dimensions. I can't really make one in 3 dimensions, very easy. But I have sepal length versus sepal width over my X space. And this is my KNN classifier. This is what it learns my X space, the classification and the boundaries between the classes to be. So let's actually add on to this, because we can add on some other cool information. So I want to add on my training data, because you can see why it learned the boundaries based off the training data. So what was my training data? My training data, and train X, train Y. Okay. So let us make 2 data frames, or matrices, whatever you're going to call this. What's the best way to do this? Sepal length. I'm just going to make this train X. Okay. ggplot only works with data frames. Can't work with matrices. Blah blah blah. So I got to make these data frames. So I just want to set these up correctly. Okay. So this is all just munging data. You can see though how much of real analysis of this data is just munging data, and it's why computational skills are super important. Okay, so I want to make my width. Just want to set up data frame with x1, x2, and then what do I want? I want my y, let's call it y, to be train y. Okay. So here it is. Let's just look at the first couple columns of this. Sepal length, sepal width, y. This is my training data. I can repeat this process, and I can do this for testing data. Test, and all I'm going to do is replace train here with test, and I'll get a similar data frame. Okay. Why did I do that? Because I want to add this on to my plot I just made, my really cool plot with all my boundaries. And because it will allow us to see why the KNN classifier learned those decision boundaries in the way it learned them. So I'm going to add my training data points. So I pass in as my data to ggplot. I pass in my training df, and then I want my aesthetic to be, what do I want? Let's think. Let's try that. See what it plots. Ah, that's not good. Pred not found. Oh, okay. Okay, let's just screw around with this. We want it similar. I'm going to not inherit this aesthetic setting from the previous. I'm going to reset this. I want my x for these points. I want to add in my training data as points. I want the x to be sepal length, y to be sepal length, and I want maybe for now, let's not make them colored. Let's just go like that. Let's try that. Okay, here we go. There are my training points in black. That's all I've added on here. And what I probably want to do is let's set the shape of these training points to be the class. So Setosa is circle, triangle is versicolor, and Virginica is square. So the different colored regions are so if I give you a point over here, it's predict Virginica. Give you a point here, it's going to predict Setosa. If I give you a point here, it will predict versicolor, right? Why? This is my training data. As you can see, all the KNN does is says if I'm here, remember our K is 5 in this case. The 5 nearest neighbors apparently are the Setosa, so it predicts that. But if I come over here, my 5 nearest, I guess, are going to be some of these close by Virginica, until I start to move over here too much, and then my 5 closest are going to swap over to versicolor. Notice I'm somewhere like here, there are some misclassifications of the training data. It doesn't get it perfectly. We could get it perfectly if we set k is equal to 1. That's silly. But so if I'm here, say the nearest are maybe, these two Virginica, this versicolor, and some other Virginica. So it predicts Virginica, which seems reasonable. And so you can kind of see how it learns. These are the regions. This green region is the region where the closest points are this kind of mass of the versicolor. Over here predicts Setosa because those are kind of highly concentrated. You can see that the Setosa are well separated from the other two classes. That's why it gets them very, very, very accurately correct. Versicolor and Virginica, apparently, at least by sepal length and width, are more similar, and so it gets it more wrong, and the decision boundaries are a little more complicated. Notice here we have this little island of green, and generally speaking, these are kind of non-linear boundaries between your classes. So we'll talk about this in lecture 9, but you can kind of see visually why KNN predicts at each of these points. Why it predicts green over here, why it predicts versicolor. Well, that's kind of the mass of the versicolor. So that's a nice little visualization of what it's doing. And you could even add on the training data. So yeah, let's add on the training data. I think we can do this. So let's just recapitulate this. Let's see if we're going to run out of symbols here, but we can, instead of adding on just the training data, we could add the testing data. So we can also add the testing data. And I'm going to instead I'm going to fill in the points based on their class for the testing data. See if this works. Okay, so it adds the testing data. but it doesn't quite get it right. Let's see if we can fix this. So I think if we, for my point here, I change the shape. So PCH is the shape. If I change it to like 21, is that going to work? Yes, okay, that worked. Okay, so the filled in circles, the dark ones, the black ones are the training data, and the circles with the colors filled in are the testing data. So for example, we have all these red circles over here in the red region, which means those red circles are predicted correctly. We have some green circles here, which means the true class of the circle is that green. That looks like it's green, right? The true class of the circle is versicolor, but it's actually in the Virginica blue region, so it's wrongly predicted. Or, we have a blue circle over here. True class is Virginica, but it's predicted as versicolor. We have some green, the green circles over here, which are correctly predicted. So this is kind of a nice little visualization of what's going on. So I really like this kind of coding idiom for visualizing how these classifiers work. Okay, so in the last couple minutes here, let's just wrap this all up into some function, and we could change our value of k to our classifier, which I had pulled that code out at some point, didn't I? Now I can't find it. Well, let's go grab our classifier fitting code. Here's our fitting code. And then we need to actually remake this grid, right? Okay. So I think we can just wrap this all up in a function. Oh, come on, copy. Let's go. Copy this. Copy. Okay. Hopefully that copied. This is like old person hour with technology here. Okay, so I think this works. Just move this over. Okay, so let's call it plot k. It's gonna be a function. I'll have one argument k, and that will be our k for the KNN classifier, and then we'll plot it. Okay, so if I call plot k 5, that should give us the plot we just saw. Gorgeous. But we could try other things, right? Like, what if I set my k to be 1, right? We know what that does in the regression case, and it's going to do a similar kind of thing, where it's going to just perfectly learn based on, it's going to set the boundaries very flexibly based on the training data. Whereas if I go with a high value, how many points do they have? About 30, let's say 30-ish. It's going to have kind of much more. So here's the point. First of all, let's just go with 31. I don't know, even that is weird. So you see this speckling here, which is not too great. So what happens is that if you have a tie, KNN just flips a coin. So it might even plot differently if we run it over and over. Yeah, it does. So you see how some of it's changing? It's because it's flipping a coin. So let's bring it down to like 15, let's say. Okay, so here, high value of k. First point I want to make is high value of k, we have these less flexible borders. They're more kind of smooth. If we have a low value of k, like 1, we have these highly intricate borders here. You'll get some of this kind of speckling going on, especially if you have like even values. Like if I do k is 2, you get some of this because there are, if I have the 2 nearest neighbors, you could end up in a tie very easily. And so what KNN does is just flips a coin if there's a tie in the majority class, and so you get some of the speckling. And if we go with, how many points do we have? 33. So we can get different pictures. You can play around with the values of k, and you can see lower values of K will give you more flexible things going on here, and higher values of K, what was our maximum? Yeah, right. Okay, so here's K is 50. Maybe we get 50 overall, right? So what's going on here? If I say fit with the 50 nearest neighbors, turns out in our training data, the majority class is Setosa. And so if it's just the 50 nearest neighbors, Setosa is always going to dominate. Because if you look at all points, the majority is going to be Setosa for the training data. So you get some kind of weird behavior going on there. If we look at something slightly lower, let's say like 45, yeah, so you have this kind of Virginica is never predicted, and you get some kind of weird things going on. Anyways, you guys can play with this. I think it's fun. It allows you to play around with KNN, and you can kind of export it to other data sets. The idiom here of how to plot this is super general, and we'll see it more throughout the course, but we're kind of at time, so let's stop there.